Well, thank you very much for the introduction. Yeah, I'm very excited to be here today to talk about some of the work that we've been doing at Cubist. We are a startup in the Web3 ecosystem that is working on tooling for Web3 development. We have a diverse set of backgrounds in academia as well as industry, in like security, fraud detection, programming languages, and verification. And so given our background, we are focusing on tooling that makes developing Dapps more secure while still keeping the tooling easy to use. And so in this, so far we've been mainly working on two products. One is a cross-chain SDK, and the other one is a key management solution. And so today I'm going to basically give you a sneak peek of our upcoming new version of the SDK. And then Riad, our CEO, is going to talk a bit more about our future directions and how we plan to integrate the different products that we are working on. So earlier this year, we released the first version of our cross-chain SDK. And basically, the goal of this SDK is to make it easy to develop dApps that work across different chains. And basically, the main job of our SDK is to take care of the interfacing between the two different chains. Between the different chains. And instead of building our own bridging solution, we are bridge agnostic. And so what we've been focusing on is basically making it easy to integrate with different bridge providers. Additionally, what our SDK allows you to do is make testing locally fairly straightforward. And so earlier this year, we released the first version of the SDK. At that time, the Soroban ecosystem wasn't quite as mature yet, so our focus has been on EVM-based chains. But with the upcoming release of our SDK, we are going to bring two main new features. One is integration with Axelar as a bridge provider, and the other one is Soroban support, which I'm going to demo right now. What that looks like. So here we have a simple Soroban contract. I'm sure you've seen something similar a ton at this conference and maybe on before when you looked at Soroban. So it's just a simple contract that basically allows you to store a number. Now, let's say you have this contract, but you want to somehow interface with this contract from a different chain. So this is basically where our SDK comes in. And so without modifying the Soroban contract, we can write a contract that gets deployed on Ethereum that then calls methods on the original contract. And so the way this works is that each SDK project has this configuration file which basically kind of tells our SDK about the kind of contracts and about the kinds of chains that you're interested in. And so in this case, as we can see here on the right, we basically just say, well, we have contracts for Ethereum, and we have contracts that get deployed to Stellar, or yeah, so some Soroban contracts. And so here, we basically just say, well, we have this contract that I showed you previously. And in addition, we have this contract called ethstorage.sol, which is just a Solidity file that makes the call to the Soroban contract. Now, if we take a look at this contract, it looks almost like a regular contract. Like the only thing that looks maybe a little different here is that this import statement, instead of like importing an existing contract, it actually has this little prefix like stellar : and then mentions what kind of the name basically of the contract that we would like to import. And then from there on, we just use that contract as if it was a native Solidity contract. So we can call method on this contract. We can initialize it with an address and so on. But of course, this won't compile, right? So this is where our SDK comes in. Namely, our sort of build phase, like our SDK, when you build a project, it basically consists of 3 phases: the pre-compilation phase, the compilation phase, as well as the code generation phase. And instead of doing them all at once, as you would usually do, I'm going to do them separately. So I'm first going to do the pre-compilation step. And what this will do is it will generate the shim files, is what we call them, which basically are those Solidity contracts, like here, Stellar Storage, that kind of mock what the interface of the Soroban contract looks like. And so if we go and take a look at that file, we see it's like, it has this store method here. And basically, what it does right now, since I've configured just a sort of a dummy bridge provider, it just emits an event if this method is called. And so this file is automatically generated. That's why it looks kind of ugly. But yeah, you don't have to write any of this. And so if you would want to change bridge providers later on, you could simply change this one field here to say something like Axelar, and we would, instead of generating the shim contract that I showed you before, we would generate a different contract accordingly that would call into that bridge provider. So after the pre-compilation phase, there is the compilation phase, which basically just calls, in this case, it calls just a Solidity compiler to basically compile the Solidity contracts together with the shim contracts. And then as a final step, we do the code generation. And the code generation basically generates bindings for the different contracts, as well as some like helper code. It basically generates 3 files. It generates interface, it generates interface files for all the contracts, as well as sort of the main project, like code to interact with the project as a whole. And you don't have to like look at the generate the code in detail. It's kind of ugly, but yeah. So as the sort of final step, we can now that we have this project, we can write code in Rust that actually like interacts with it. So in this case, we are going to deploy the Stellar contract. Then as a second step, we are going to deploy the ETH storage contract that we saw before to an Ethereum chain. And then after the bridge has been established, we simply call, we do one call on the ETH storage contract, and it will automatically update the value on the Stellar contract as well. And so to do that, we have to we can start some chains locally. Oh, this is a little ugly. So we can start like an Ethereum server and the Stellar server locally that we can then deploy to. So we can now run this binary, which will do the deployment to the different chains, as well as, so it's now deploying the contracts. Okay, so we deployed the contract to the Soroban local net. Then we deployed the Ethereum contract to the local Ethereum server. Then we waited for the relay, and then we finally sent the value. And now we can go in and actually see that the value in Soroban has actually been set. So we can call the contract, and we see that the value has been set to 23, which is what we did here in the ETH storage, or with the ETH storage contract. So yeah, this is just a small preview of what our SDK will look like for cross-chain development with Soroban support. And now Riad is going to tell you some more about our future plans.
Sure. Yeah, I like that. Yeah, I find that like so satisfying that it's like you can just deploy everything. It's done. You run one command. Everything's deployed on all the chains, and then like you can immediately run stuff. So it's a really nice development experience. And nice demo. It's always nerve-wracking to write that code live. Okay, so what does the future look like? So this is, I guess, the immediate future. We're going to release the Soroban version of it very soon. But after that, what are we doing? So more bridge integrations. So we want to, as Andres pointed out, you have this configuration file, right? And in that configuration file, if I want to switch from using my test local bridge to using, say, Axelar, I change one line in the configuration file, I recompile, and I'm ready to go. Yeah, so adding more integrations is a good one. So Axelar will be in the next release. Yeah, we have more bridges coming soon. If this is something where you're developing a bridge, where you want to make it easier for folks to integrate with you, get in touch with us. We'd love to chat and learn more about it. So the other thing that we're going to be doing is adding new chains. So we want your feedback here. So we have EVM support. I think we have Solana support in a branch somewhere that'll eventually emerge. We'll see. Yeah, Soroban's coming as well. But yeah, your feedback is wanted here too. And I think actually we're going to have a bit sort of deeper, richer support for some of the Axelar chain execution primitives as well. So that'll be soon. And then the last piece that that's coming next is integration with CubeSigner. So Andres mentioned this earlier, but this is basically a way of making your sort of the other half of your development experience easier. So this is sort of once you've deployed stuff, how do you manage all of the secrets and all the keys that are used to actually interact with your contracts? So yeah, since my background is in cryptography, I get all excited about this stuff, so I might talk too fast, but I want to tell you all about CubeSigner. So just a brief overview. So you can think about this as essentially a service, a REST API that you can call, and it handles managing your keys for you. And really, there's kind of three pieces to it. So there's an API, you interact with it. It's yeah, just an easy to use REST API. We also have a TypeScript SDK, and we interact with it with Rust, and pick your language. And then there's a policy engine that sort of says this is what the keys are allowed to do. So for each key that you have, you can apply policies to that key. You can also apply policies to sort of individual identities that are accessing those keys. So you can say, you can say simple things like, this key can only send transactions to this address. You can say more complicated things too, and I'll give an example of that in a second. And then finally, the sort of core of the system is what we call a virtual HSM. It's a standard like FIPS 140 hardware security module that's coupled to a secure execution environment, an AWS Nitro Enclave. And so the idea there is that the only code that ever touches any secret key is running in a secure hardware-backed environment. And so when the key is generated, when you use it for signing, anything that you do with it is happening inside of secure hardware. And so your keys are never exposed to anyone, certainly including us. Good. So I want to give a couple thoughts on what do these policies look like, maybe give you an idea of what goes on here. So one that I think is kind of obvious and interesting is, look, if you are sending a high value transaction, if I'm suddenly trying to send like some enormous amount of money, probably my key should say, wait a second, let's see some more ID. So MFA, you can have multiple approvers, and you can set thresholds based on things like transaction size or something like this. You can also do things like limit interactions with specific contracts. So I might say, here's a key. I want to, give my intern a little bit of money to go and farm some airdrops or something, but I don't want them to do some, weird interactions with DEXs or whatever it might be. And so we can say, like, sure, go ahead. You can use, any swap you want, but the only tokens you're allowed to swap with are these, right? So you can arbitrarily limit the arguments to contract calls. You can do things like time lock signature release. So for example, you might say, okay, any transaction that's over a certain value, this transaction, we won't actually release the signature for a week, and in that time we'll notify some people and they can say no, that transaction shouldn't go through. And so you can imagine these are sort of very useful for the riskiest types of transactions that you might encounter. And then finally, things like have I been pwned integration, generally sort of Oracle integration. Before a signature is released, consult the Oracle, and if it says yes, everything's good, release the signature, otherwise don't. Okay, so those are just some ideas of kinds of things that you can do. Yeah, we'd be interested to hear other thoughts. If you have a particular integration that you think would be really interesting, risk analysis, this sort of thing, we'd be interested to hear more about it. And then, like I said, I'll try to stop myself from nerding out too much about the sort of the core piece, but this is kind of my favorite part of the system. As I said, we kind of call it a virtual HSM. So the idea is you use you get the security of a standard FIPS 140 hardware security module, but you get more flexibility and you get more speed by sort of sealing that to an enclave. So if you look into, like if you go to AWS and you say, I want to use the KMS, which is their HSM service, or you go to the corresponding one from Google or Microsoft, the range of keys that you can use with these things is quite limited. So I'm pretty sure, for example, that ED 25519 is still not supported in any of these. Maybe eventually we'll see FIPS 140 support for ED, because I know NIST is standardizing it. But yeah, so right now you basically have a choice of like the NIST curves, RSA, God forbid, and SEC P256K1 is available as well. But the performance of those things is abysmal. So for example, in AWS, you can get about 300 signatures per second from a SEC P256K1 key, which is just ridiculous. Like that's not enough. Certainly not for something where you're running, say, all of your keys, right? So this is the kind of performance limitation that you really want to work around. On the other hand, these HSMs are great from a security perspective, and they actually give really good performance for something like AES. So we take advantage of that by running the asymmetric crypto in a hardware enclave that's sealed to the HSM, which means that the only way that the HSM will decrypt the secret key is if it knows that it's talking to the hardware enclave. And so then the idea is these two together are sort of giving you essentially the security of the HSM, but as I said, the speed and the flexibility of the hardware enclave. And so, yeah, you might ask, well, hardware enclave, I've said this word a lot, SGX is something that comes to mind. Why not SGX? We don't have enough time for me to tell you why not SGX, but the short version of it is it's totally broken. Please don't use SGX. Intel has never shipped a secure implementation of SGX, and my guess is that they never will. SGX tries to do too much. It's very complicated. It has been broken many, many, many times, most recently at Black Hat this year by our good friend Daniel. So yeah, we don't use SGX and we don't think you should either. Okay, so all of our code for for what Andres showed you too, is written in safe Rust. So this means that we eliminate a whole class of vulnerabilities. As I mentioned earlier, the key generation, signing, wrapping, every operation on secret keys happens inside the secure hardware. And we actually have some functionality for importing and exporting keys too. So importing, I think, is a really important one. You've already been, running your application for a while. Now you want to, sort of shift into using something like this. You need to be able to bring those keys in. So the way that we do this is you talk directly to the virtual HSM. You get sort of a signature from it saying, yes, I am in fact running in secure hardware. You encrypt to the secure hardware, and then it decrypts, and now you have your key. But I think maybe even more important is exporting. Once you generate keys in the secure hardware, you should be able to get them out. You should be able to use them, but only in a very safe way. So the way that this works for us is we've come up with a protocol whereby you register sort of at initiation time a set of YubiKeys or hardware tokens generally. Right now we prefer YubiKeys. And you say, look, I have 9 YubiKeys and I need at least 5 of them to sign or to decrypt if I want to actually extract my key. And so then the idea is every time a key is generated or imported, we immediately encrypt to your quorum of YubiKeys and give you that ciphertext. And now you have in cold storage your key. You don't have to interact with us. You don't have to talk to AWS. If a meteor hits the East Coast, you're fine. And you can decrypt your key and go on your merry way. Good. So these are the sorts of things that we try to make easy. And in fact, it's quite easy. So for example, generating a key and then signing a transaction is 2 lines of code. I added the console log line to make it seem like more code because it didn't seem like enough. So yeah, it's really just so easy. You create a key and you can sign transactions with the key. And because we comprehend the transaction format itself, you can apply policies on the fields of the transaction, which is sort of nice. And because of the policy engine and the virtual HSM, yeah, it's quite safe. It's a nice way of interacting with your keys. And so the way that this is going to integrate into the Cubist SDK is in that configuration file, you'll just be able to point it at your instance of CubeSigner and say, here are the keys that I want to use. Here's my token. Go. And then down the road, if you, for example, if you have something deployed and you need to change which keys it's allowed access to, that's easy. You can revoke access. You can add new access, etc. Great. So. Yeah, so actually, docs for the SDK are at this link. If you want to get in touch with us about more chains, more bridges, if you want to talk about CubeSigner, all of the above is great. Please hit us up on Telegram. I promise the sentient AI really is him. Yeah, so thanks a lot for your time.
Great.